Hi, I am Sahil, and this is my walkthrough of the bike sharing demand forecast. The company wants to predict how many bikes people will want each hour, so it can place bikes and staff ahead of the rush rather than react to it. One idea runs through the whole notebook that being short of bikes costs more than having a few spare, and I will put a number on that shortly. Now, let's scroll down to the section. So the first thing to settle was which model can do this job. So here are three side by side. A baseline that just guesses the average is off by about 100 and 40 bikes an hour. Linear regression is better. The random forest is the strongest, cutting the typical miss to around 53 bikes and explaining 84% of the demand pattern. So that is the model I use from here on. Now, looking at the errors, basically, so a single average can hide a lot. So I broke the errors down hour by hour. And the pattern that stood out is that the model runs short through the afternoon, which is exactly when the city is busy. A shortage then means a lost trip and a frustrated customer. So that is where the errors matter most, right here. So now putting a cost on it. So a to show why the afternoon gap matters, I put a cost on it. I price a missing bike at 40 dirhams and a spare bike at 15. So a shortage is the more expensive mistake. It is a way to compare options rather than a real bank figure, but it turns forecast errors into something the business can weigh. Now comes the testing before we roll it out. And so the notebook also lays out how I would test this before any real rollout, right? So in the pilot design here, some stations would follow the forecast while a matched set keeps the current manual process, and I would mainly track whether stockouts drop with guardrails so nothing else slips. Now, moving on to my three modifications. So, the first modification here, the cost is only my estimate. So, my first change test uh, tested how much the exact numbers matter. I ran the costs from a small gap up to a large one, and the conclusion held every time. Under forecasting stated the bigger cost throughout. So the plan to guard against shortages does not depend on me guessing the price correctly, right here, as you can see here in the chart as well. Now, my second change uh, went back to those hourly errors. The notebook assumed the costly hours were the usual rush, morning and evening. But when I ranked hours by their real cost, the expensive ones were the late ones right here. So matching the rush only on 1 hour. So I cost by about a quarter. That saving is a best case since it was tuned on the same data, but the direction is clear, right? As you can see in the chart and the tables up above. Now, my third change basically tests whether the model holds up over time. I trained it on 2011 and asked it to predict 2012. The way a real forecast works is the error nearly doubled and the score dropped because ridership grew about 63% in a year. So the model could not keep pace and kept under supplying as the city grew. Now, putting that together, the random forest is strongest, and the afternoon buffer is a practical rule the team could use now. The main risk is that the model loses accuracy as the city grows, so it cannot be left running on its own. So I recommend a limited pilot in a few zones with a set schedule to retrain or retrain on recent data and clear success targets agreed in advance. If it works there, then scale it up. Thanks for watching.